think of more questions for this session. But indeed, in life, let's just go to the next one on reinforcement learning and control, roughly. That will be chaired by Stephen Brunton. So Stephen, I know you are there. The floor is yours.
Hi, thank you. And welcome everybody to this session. Congrats on sticking it out to the last day of this excellent conference. And so I hope everyone's enjoying the great talks. I know I certainly am. So I'm Steve Brunton, and my co-host Urban Faisel is also here. And we're really excited to introduce this fantastic array of speakers on a very important topic at the interface of machine learning and control theory. Again, really excited to have a discussion at the end, so we're going to try to keep everyone on time. Urban, do you want to take over?
Yeah, absolutely. So, as Steve just mentioned, we have really exciting talks today. It's 5 in total, talking about reinforcement learning and control methods and applications. And our timeline for this session is quite compact. So we have 4 to 5 minutes short spotlight presentations, and then followed by a large Q&A. And I suggest, as it was already done in the previous session, to post your questions in the chat or in the Slack so we can collect all of them and then organize the Q&A. Okay, so our first speaker is Yuha Xu from Stanford University. And we will talk about borrowing from the future, addressing double sampling in model-free control.
Okay, thank you for the introduction. So I'm going to introduce a new algorithm to alleviate double sampling problem in model-free reinforcement learning. So first, one of the main goals in reinforcement learning is trying to find the optimal value function among all possible policies. So here we assume the state S is a continuous state space, and action A is from a finite discrete set. Here we parameterize the value function by a parameter theta. So then finding the optimal value function Q is equivalent to solving this minimization problem, basically minimizing the norm of Bellman residual. Here, this T star is a Bellman operator. And notice there is a conditional expectation. And this expectation is on the next state, conditioning on the current state, which we will use later. Here we assume the transition dynamics is a discretized SDE with a small time step epsilon and drift term alpha and diffusion term sigma. So in the model-free setting, usually the transition dynamics is unknown. So we're only given a trajectory which is generated from this transition dynamics. And we use this trajectory to solve this minimization problem. So what we do is we use the SGD. So we need to calculate the gradient of the object function, which is the Bellman residual times the gradient of Bellman residual. And as we said before, the Bellman operator has so this term has actually 2 independent expectations on the next state. So in the unbiased gradient descent, stochastic gradient descent, we will require 2 independent samples for the next state. So this is called double sampling problem. Why? Because, so for the first sample, we can easily get it from the trajectory. However, for the second sample, it's usually unavailable because remember, we are in a continuous state space. So it's hard for the trajectory to go back again to the same state and generate an independent sample again. So what we do is we move 1 step forward. This 2 step can be easily obtained from the trajectory. And then we borrow the future step to the current state and approximate the second independent sample for next state by the current state plus the future step. So we can imagine that when this transition is smooth, then this two step will be similar to each other. Then this will be a good approximation. And we can also generalize this method to multiple future steps. We borrow the two steps and average them together and then add it to the current state. And we also have a pretty good theoretical guarantee for this method. So the main assumption is that we need to assume the underlying dynamics change slowly with respect to actions. So basically, we require the diffusion term and the drift term. The variation of these two terms in action space need to be bounded by a constant. Under this assumption, we can prove the difference between the PDF, the probability density function of our new method and the unbiased SGD. They are exponentially decay in time and finally stabilize at an error of order epsilon times this term. This term is the smallest Bellman residual that unbiased SGD can achieve. So this is all for my talk. Thank you.
Awesome, thanks, Yuha. It's great work. Then our next presenter is Willem Gispen from University of Cambridge, who will talk about ground states of quantum many-body lattice models via reinforcement learning. Oh, Willem, we can't hear you.
We don't hear anything. Are they aware?
In the chat.
Looks like your microphone might not be
Yeah.
on.
Hello, hello, we can't hear anything. I hope the person is not speaking without realizing it should not, right? Now we talk a lot.
So let's give it another maybe 30 seconds, and if not, we can just reverse the order of an author.
Yeah, I think that's a good idea. We can come back to this one when they clear the issue.
Okay, Willem, so if it's okay for you, we would continue with the next presentation and then you would be next, if that is okay. So the next presenter would then be Alex Ling from UCLA, talking about decentralized multi-agents by imitation of a centralized controller.
Oh, yeah. Can you hear me?
Yes.
Okay, cool. Thanks for the introduction. Let me, so yeah, today I'll be talking about decentralized multi-agents by imitation of centralized controller. Yeah. So, reinforced learning is, of course, a single agent reinforced learning algorithm. And here I'm talking about a multi-agent reinforced learning algorithm. So what's the difference, really? Well, the difference is there are multiple agents, I suppose. But also, there's also a difference in how things are run. In single agent reinforced learning, you have sort of an agent, and then they receive a state and reward, and then they take an action that goes through the environment, and then they receive the state and reward again. But in multi-agent reinforced learning, we have a bunch, like multiple agents here that each receive their own sort of state and rewards, and they also take their own actions. These actions go through the environment, and then the environment, this has an effect on the environment, and the interpreter takes this effect and then gives the agents each their own states and actions. And a key feature of this is that everything is decentralized. So agent 1 receives S1R1, agent 2 receives S2R2, etc. And so basically each agent is only able to see its own local observation. So that's a key feature of that. And another key feature of multi-agent reinforced learning is that from the perspective of each agent, actually, the whole environment, which includes the other agents, is also non-Markovian. So in this sense, it's very different from single agent reinforced learning, where a lot of the assumptions are that it is a Markovian setting. So I guess you can think of it like in golf, maybe that's like a single agent reinforced learning algorithm. Okay, so if you like suppose that there's no wind in golf, then if you take then like depending on where you are, it's pretty clear what the best actions you should take, assuming no wind. But you know, if you look at multi-agent reinforced learning, perhaps a better example is like soccer, where maybe like I can do a little trick to hit the ball and get past you. But the next time I try to do that, you would have already learned. So you know, the setting in that sense, because other agents can learn, then the whole environment is non-Markovian from the perspective of each agent. Okay, so those are some like the key features of multi-agent reinforced learning, and the non-Markovian part being a big deal in that. And so, you know, yeah, in our paper, we present a way to deal with this non-Markovian part, and also a way to just learn cooperative multi-agent reinforced learning in general. Cooperative multi-agent reinforced learning is basically multi-agent reinforced learning. Sorry, let me go back a slide, where the rewards are now all the same rewards. So in that sense, the reward is not based on any individual, but based on team. So anyway, yeah, we go back to this diagram. I talk about other methods in my video slides, but here I guess I'll just, for the interest of time, talk about my method, where it's centralized expert supervised multi-agents. Where basically we first train a centralized expert, treating the whole problem like basically concatenating the states and rewards and also the actions. And once we train the centralized expert, then we decentralize this centralized expert to the multi-agents by doing supervised learning, where now we let the agents run through the environment, and they receive an observation O, and they also take they receive an observation O here. State and observation is the same, but yeah, well, I go into that in the video slides. But anyway, so then this observation goes to the centralized expert as well as into this data set of joint observation and expert label action pairs. And then you do supervised learning in here, where O1, A1 stars for agent one, and so on. And then in the video slides and also in the paper, I go through some experiments. One of these experiments is cooperative navigation, where you have all these multi-agents and you want them to all cover the landmarks. So in this here, the reward is basically, you look at each landmark and you find the minimum distance agent. And then you take a negative of that and you sum that all up. And I also have some collisions with this environment too. So we also subtract the number of collisions, and that's your reward of each time step. And this will encourage each agent to cover the landmarks. And then I talk about that. And I talk about how our method is better in terms of sample efficiency than the other methods. And also it receives a better optimum. And I also have another more complicated experiment in the StarCraft 2 environment, where I show that our method is better than independent Q learning. And SESMA is able to achieve high win rates. So not only do we measure the reward, we also measure something more important, which is the win rate against opponents. I mean, the opponent here is going to be the heuristic AI coded by the developers of the game, and on the hardest difficulty set. But yeah, please check out the paper if you have more questions or are interested. Thank you.
Awesome, really cool work. Thanks, Alex. Now, Willem, should we try again with your presentation?
Can you hear me now?
Yes.
Okay, so my on-screen name is a bit weird. It's not my name, but let's just, it works out like this, so that's great. All right.
Perfect.
Sorry, I just have to restart everything. Sorry for the slight delay. But thanks for waiting for me. So I'm here to present work that I did together with Austin Lamacraft, and it's actually an application of reinforcement learning in quantum physics. So we're trying to numerically study these quantum lattice models. And
you're going to share some slides, Willem? Sorry to interrupt.
Huh? Sorry?
Are you sharing slides?
Am I?
We're not seeing. Okay, now we are. Yes, thank you.
Thanks. So you can see my slides now. Great.
Yes.
Yeah. So I'll just start over. That's fine. So this is, as I said, this is work I did together with Austin Lamacraft, and it's an application of reinforcement learning to these quantum lattice models. And these lattice models are useful simplifications, and we use those to understand phenomena like superconductivity, magnetism, or even some kinds of quantum computation. And typically what you do, what a lattice model is, you say that all your particles are confined to a lattice. So this is like your straight lattice where your particles are on. And your model describes the interactions between the particles. So that's your Hamiltonian in the system. That basically gives the energy of your system. So what I'm interested in is the ground state behavior, so the zero temperature behavior physically. And that's what you need to do is minimize energy. So you need to minimize this sum of potential energy and of kinetic energy and potential energy. So this sort of balancing act is a bit similar to what is found in reinforcement learning, specifically where, as we'll see later, the potential energy is related to rewards, and this kinetic energy is related to regularization. Another thing that's a bit similar is that this amount of configurations you can get in these lattice models is exponentially growing with the amount of particles you have. So that's similar to these very large state spaces you can get in games like Go. So physically, this balance between kinetic and potential energy is also captured in this Feynman-Cag representation of the ground states. So that basically says that the ground state wave function can be expressed as an excitation over trajectories. And these trajectories are then generated by this kinetic part of your Hamiltonian, but they're also weighted by the potential part of your Hamiltonian. And what we show in the paper is that you can transform this and translate this to a soft-Bellman equation. So the equation governing reinforcement learning. And this potential energy directly translates into the rewards of your reinforcement learning problem, whereas the kinetic energy translates into an entropy regularization. So this is a maximum entropy reinforcement learning where you have soft Bellman equations. Instead of like the usual maximum and maximum here in this soft Bellman equation, you have a soft maximum. So once you have this translation, you can then use reinforcement learning methods and algorithms to actually study the quantum system. So what we have done, we've approximated the action value function with soft Q learning, this algorithm by Noja and others. And this immediately gives you one advantage as opposed to other optimization methods for quantum states, is that the update steps are much faster. And if you have done that, you can then translate back and do the inverse transformation to get your wave function back. But even better, you can also follow the policy that you learned with your reinforcement learning algorithm to directly sample the state of your ground state. So these samples you need to calculate actual observables and properties of your ground state. And because this policy knows where to go, it has learned what are good areas of phase space, it has a lot faster sampling of your ground states. All right, so what I've shown you here is how these quantum mechanics can be related to reinforcement learning, and specifically how it leads to new optimization methods for these neuroquantum states. And two benefits of this approach may be faster optimization steps and faster sampling of your ground states. Thank you.
Great, thanks, Willem. And then our next speaker is Chahao Yao from University of California in Berkeley, and we'll talk about noise-robust end-to-end quantum control using deep autoregressive policy networks.
Thanks. So first, it's about the background and the problem setup. And the problem we consider here is the state transfer problems, which is to go from the initial state, which is either the prepared quantum state, and go to the target state, which is the ground state of the target Hamiltonian. And the ansatz we use is a QAOA ansatz. So that is one specific quantum variation of quantum ansatz that is alternative between the two Hamiltonian, and the two Hamiltonian is come from the physics model. The physics model we consider is one, the IC model, and another, the Heisenberg model, which is commonly used in this setting. And the objective we use is the energy or fidelity. So, and the optimization is going to minimize the energy or maximize the fidelity. So one very important concept in our paper is the counter-diabatic driving method. So what is CD? So in the adiabatic computation, you evolve with the quantum Schrödinger equation, and in the CD, you evolve with the effective Schrödinger equation. So that is, you go to the rotating frame and then you derive the effective equation, you'll get this equation. So that means the idea of the CD is to compensate the Hamiltonian with this auxiliary terms, and the effective Hamiltonian will go back to the original H0. So then the dynamics there is stationary and no transition will occur. So here is an analog of the adiabatic computation and the CD driving. So in the adiabatic evolution, you have to be slow. And if you go fast, the cause is the water will spill or some population will excited. So that's for the CD is you apply the opposite force and you can go fast in that case. And here are some examples in the single qubit and like a spin chain case. And our idea is to combine the CD idea with machine learning or reinforcement learning. And here, the network we use or the model we use is an autoregressive autoregressive network, which was also mentioned by Professor Kramer from last workshop and today's by Chen Xiao Li about the dynamic systems. So, and this allows you to sample from this policy and also do the policy updates to adjust the weight. And here, to optimize that, we decompose the network into two parts, which is the continuous and the discrete degrees of freedom. And here we have the policy gradient formula here. And we also use the maximal entropy formula, which is also mentioned by the William. We have the entropy regularization for the discrete and the continuous one. And now I'm going to share you with some results for our work compared with different algorithms in terms of the noise. So yeah, noise is quite an important aspect in the quantum computation. This Newton. So with so you can see with the noise, and especially when the noise level strength is high, so the CDQIOA will like decays, but the IOQIOA still can maintain a very good level. So yeah, so here is a summary of our work. So we derive a discrete and the continuous hybrid optimization IO algorithms. So the framework is quite versatile and also noise resilient to different kinds of noise. And then our onset is based on the principle of variational counterdiabatic driving. So which is not just selecting a different kind of gate, but the gate is actually have some physical intuition inside. And so last is our generalized QIOA onset can be expressed in terms of in the quantum computation problem. Yeah, thanks for the listening.
Awesome, thanks, Jiahao. And then our last presenter is Andrea Agazzi from Duke University, who will talk about temporal difference learning with nonlinear function approximation, lazy training, and mean field regimes.
Yes, thank you. Can you hear me?
Yes.
Yeah, okay. So thank you very much. So today I will talk about a recent work with Jianfeng Lu on the use of nonlinear function approximation with reinforcement learning algorithm called temporal difference learning, with particular focus on the behavior of wide single layer neural networks, both in the lazy training and in the mean field regimes. Now, the objective of temporal difference learning algorithm is to learn the so-called value function, which for a given state space, reward function, and a certain transition kernel P on the state space inducing a certain dynamics maps an initial condition S to the expected sum of future rewards under the dynamics being considered for the given initial condition S. Now, this function essentially quantifies how good a certain initial state is under the given dynamics, is central in reinforcement learning, And it is known to be the fixed point of the so-called Bellman operator that is written here, which is known again to be a contraction in a certain weighted L2 space. Now, using this knowledge, one can, it's natural to guess a certain algorithmic update for an estimate of the value function, which updates the estimate infinitesimally in the direction pointed at by this Bellman operator, which again is a contraction, so it's an algorithm that should converge. Now, if one is instead not free to move in function space, but has a model, we have to project this update on parameter space, like it's written here. And it is known that because, unlike in the supervised learning setting, this algorithm is not a gradient flow, this projection can give some unwanted phenomena, such as in this case, which is a famous example of divergence. We see that we have the vector field represents the update, the temporal difference learning update in the function space. But if we, it's not a gradient flow, but if we have a nonlinear model, like the spiral here, the projection will actually diverge despite the functional update being convergent. Now, in this talk, we are going to consider a specific family of function approximators, which are single layer neural networks of width n, for n going to infinity. And we want to know, well, whether this kind of phenomena occurs for these approximators, or more generally, how do wide neural networks behave under temporal difference learning. It is known that these models behave in a very different way or in different regimes depending on the initialization of their parameters. So we're going to study two and contrast two different regimes. The first one is the so-called lazy training or neural tangent kernel regime. And to study these dynamics, we consider a scaling of the approximate value function by a large parameter alpha. So graphically speaking, the effect of this scaling is essentially to linearize the model at initialization. This was known in the supervised learning setting. And in particular, as alpha goes to infinity, the model will converge to a reproducing kernel Hilbert space that is tangent to the original model at initialization. Like this, it's a flat space. This is represented by this update, which is simply a kernel method. And this removes one of the two problems that were leading to divergence, which was the nonlinearity of the model. So what we can show in this regime is that in the overparameterized setting, we have exponential convergence to a global optimizer, so to the actual value function, while in the underparameterized setting, we are not sure, we cannot guarantee that the actual value function is in the limiting reproducing kernel Hilbert space. So all we can guarantee is exponential convergence, but to a local fixed point or to local minimizer of the dynamics. Now, this linear dynamics has to be contrasted with the so-called mean field regime, also explored recently in the supervised learning setting, where the state of the network is expressed as the empirical measure on the weights of each of the neurons by exchangeability of these weights. And the dynamics of this empirical measure is captured by a partial differential equation of the Vlasov type, so a nonlinear partial differential equation. So this is a much more nonlinear setting, and what we can show is a convergence result showing that sufficiently wide neural networks behave essentially like the law of their parameters as evolved through this partial differential equation. And the second and most important result shows that for sufficiently expressive neural networks, the limiting points of the dynamics under this partial differential equation are optimal, so that the sufficiently wide neural networks have limiting points under the temporal difference learning algorithm that recover the value function. So this can be summarized in these numerical results, where we see that in the lazy training regime, we have exponential convergence to the global optimizer in the overparameterized setting, but in an underparameterized setting, we are stuck on a reproducing kernel Hilbert space, so we can only show local convergence. While on the contrary, in the mean field regime, we are able to leverage the full potential of the universal approximation theorem. So we have convergence to limiting points that are globally optimal, but we have a worse grasp essentially on the convergence of these dynamics because of their nonlinearity. So this picture is essentially quite similar to the analogous results in supervised learning, but that we extend to the reinforcement learning setting where we don't have the gradient flow structure to leverage. Thank you very much.
Awesome work. Thank you very much, Andrea. So now we have 20 minutes time for Q&A. I see there are a couple of questions already in the chat. You can just ask more question or raise your hand or just unmute yourself for the Q&A now. Okay, so maybe, I see.
I didn't understand. So do you want us to unmute ourselves to ask questions?
Yeah, I think ideally you can just unmute yourself, ask your questions, and so we can have the most like smooth conversation.
Okay. So yeah, first I would like just to congratulate all the authors. I mean, I think these papers were all awesome. So let me just maybe start from a question for Yuhua, the first speaker. I was just curious if you could tell us more about how general, what are the assumptions that you require on your scheme so that I can use it. So for example, I mean, since you are taking difference of states and then bringing them somewhere else, I was wondering, you know, how would one do that in a discrete state space, for example? So can you comment on this?
Yes, so we actually have an example in our numerical experiments that we apply our algorithm on the discrete space. So the key idea here is that the underlying dynamics is smooth in the space. So even if it's a discrete space, but if it's a discretization of like a circle or a whole space, as long as it's a smooth transition, then it still works. So the point is, so the difference probably will end up in a state that is not belong to this space. Then you can just go to the closest state, right? If it's as discrete state space.
So there's an underlying assumption that there's an underlying homogeneous space, right? So even if you are in a discrete state space, it's okay. Okay, understood. Yeah, that makes a lot of sense.
Mm-hmm.
It looks like there's another question for Yuhua in the chat. So in the setting of choosing the action according to a probability, what is the corresponding smoothness condition?
Yes, it's also a very excellent question. So if the policy is a probability, then basically we need to assume this policy is continuous on the state. Does it make sense to you? So basically, so the policy, the probability depending on action and the state, right? And the probability is change slowly with respect to the state. That would be the smoothness assumption.
Thank you.
May I go and ask again? Yeah. So a question for Willem that I found it quite impressive that one can connect. You start to use RL for such an daunting problem. So I was just maybe wanting to hear more about, in order to make this thing effective, how can you parameterize, how should you parameterize the Q function? And do you need to start dealing with the sort of like ansatz parameterizations that we saw a little bit about yesterday about how one can use neural networks to parameterize a wave function?
Yeah, so I didn't really say anything about function approximation, that's right. But what's really done in these neural quantum states for lattice models is to use convolutional neural networks, just deep as well, because they're very convenient. All these lattice models have all these symmetries, which are perfect for convolutional neural networks. The lattice models have translation symmetry, and sometimes people even build in like rotation symmetries as well into these networks. So we use like deep convolutional neural networks for that. And one other thing that's quite useful is that physically you expect size, like the distance, to actually matter in lattice models, and these convolutions, because they stack up, they also capture this like correlation quite nicely. As in relation to George's presentation from yesterday, as far as I understood, his method could be actually coupled to a variational method. So it could even be possible to couple his wave, his approach to his approach, like to use them actually together. And these actually things go both ways probably. That maybe with this connection, George's like these support states, for example, that you mentioned, could be useful for reinforcement learning. That you sort of identify states that are most informative. That was what I was thinking about the connection to George's work. Does that answer your question, Joe?
Yeah, I mean, I feel I might need to learn more about like the lattice aspect, because yeah, in my mind, there's in George's presentation there was no lattice, at least as far as I could see. So maybe there's something important that I'm missing in, that is very specific in your setup. For example, this, you seem to be using quite a lot the grid structure, right? The fact that you can share weight across different sites, and this is not something that a priori one could do without the lattice structure, correct?
So actually all you really require for reinforcement learning formulation is that you have discrete. For this reinforcement learning formulation is that you have discrete state space. So your quantum state space is discrete. I think George's was actually discrete as well.
Yeah. Okay.
But so let's use these convolutional neural networks, and it's of course very useful if you have square lattices.
Yeah.
Thank you.
Great. Thank you. Yeah.
Yeah, hi. I have a question. So this is Alexi. I think so. I didn't think. Congratulations for the nice work. So, but I didn't. In this case, I didn't see the ground state energy. Do you assume that you already know it, or is this computed on the fly as well?
Oh, so for well, no, it's just completely unknown. So the state's unknown. So we tested it for just a small Ising model, 6x6 Ising model, and it's like it works. Like we haven't pushed it to the limit yet.
Oh no. My question is more like, so in the formulation on the slides, I didn't see, for example, in the Feynman-Katz formula, there's no energy in it. Is the energy, ground state energy, supposed to be there in the exponential, or?
In the Feynman-Katz formula, you mean?
Right. Yeah.
Or, yeah. So yeah, it depends on you can put it back in there as well, but you don't need to know it you don't need to know it for the reinforcement learning formulation. It basically, in reinforcement learning, you have this, if you have like this infinite time setting, then you have this constant factor which constantly goes from your value function, if that makes any sense to you. So that's basically, you don't have to know the ground state energy, just like you don't have to know this constant in these infinite time reinforcement learning settings. Does that answer your question?
Yes. I'll take a look at the paper. Thank you.
Yeah, thank you.
Yeah. And I also have a question for Andrea. So about nice work with Genfo. So I mean, so I guess in the in most of the mean field work, right, you typically optimize some kind of energy, right? And this energy function, essentially, you write this as a Wasserstein gradient flow, and well, I mean, then you prove certain kind of convergence. In this IL setting, in the mean field region you're talking about, do you have a similar energy, or you don't need the energy?
So in the mean field setting, there is an idea, yes. So for the n going to infinity results, so you have to show convergence of essentially propagation of chaos, right? You have to show convergence of the dynamics in the infinite width limit. To do that, we actually use some, we have leveraged some results by John, but you do have a notion of a quantity that is similar to an energy, so that you cannot grow outside of a certain value, more than a certain value, right? So there is a similar notion, but the proof is different. You cannot essentially you don't get the stability of the dynamics. You don't get it from an energy, so that you can just look at the sub-level sets of that energy and work with that. You have to be a bit more ingenious and look at an analogous quantity, but which is not an energy.
Okay, thank you.
Now, if I may also, like now that Andrea is answering, congratulations, very nice work. I was wondering if you have thought about that's something I tried to post, kind of a separation result that highlights in this particular setup the advantage of the active dynamics as opposed to the lazy dynamics, in the same spirit of the separation results that one has in supervised learning?
Yeah, that's a great question. So I don't know that I know perfectly the literature you're referring. I know of some results. I don't know if there are some in particular that you're thinking about. But in this case, for reinforcement learning, I think the separation at a very high level seems to be very similar. That in the kernel setting, you don't seem to be learning features essentially, right? So if you're lucky and you get the reproducing kernel Hilbert space right, then you can get to the convergence you want. But so this is only part of a reinforcement learning procedure, right? One wants to learn the value function and then wants to learn the policy maybe on top of it, right? For example, by actor-critic methods, some other approaches. And in that case, it's I would say it's maybe some wishful thinking to think that your value function will always be in the reproducing kernel Hilbert space for all the family of policies that you develop. So definitely for some practical purposes, I would think that the mean field regime seems to be a more promising regime to work on. At the same time, as you know, we don't have estimates on convergence or guarantees of convergence for these dynamics. That's maybe more of a theoretical question, right? I mean, these dynamics seem by all means to converge in all numerical experiments that I have run at the very least, but there are no proofs for that. So that's made as an assumption usually. But yeah, I don't know if that answers your question in any.
Yeah, it's interesting insight. Yeah, thank you.
And I have seen, I didn't know if I should answer on the I mean by messages or by live, but I've also seen your other question, which is also interesting. I don't know the answer to that. In terms of sample complexity, our work is in the ideal setting where you have infinitely many samples, right? Where you can evaluate that expectation perfectly well. I don't know how, in terms of sample complexity, the two distinguish themselves. Is there maybe I can ask you a question? Is there a difference in this sense? Is it known what the difference in this sense is in the supervised setting?
Yeah, no. So convergence in time is convergence in time is a pretty delicate issue. So there are some bounds that are mostly developed by Leonik Shita, who was a chair 3 days ago. So there are some bounds that are give you some guarantees of convergence in time that are of the flavor of 1/t or log t over t. But the other, of course, this has to be combined with the convergence in n, right, in the number of particles, which is yeah. So you get problems coming to you like from all directions, and it's yeah. I think it's still like a pretty much as you were saying, a theoretical tool that we can use to understand like behavior of these large systems, but there are still many obstacles before this thing can actually be super useful, right, to explain experiments. But I think it's it's an important question to keep pushing.
Absolutely. Thank you. Thanks for the nice questions.
This is a great question and answer discussion so far. Any other questions from the audience? I have a question for Alex, actually. So I was very interested in this multi-agent RL. And I guess I'm wondering if you have any scaling results with your kind of algorithm. I know some of these are pretty hard to derive analytically, but I'm just curious if you can comment on that.
Oh, you mean like scaling in terms of the number of agents?
Yeah.
Oh, well, we don't have any results like that yet. But yeah, that would be very interesting in terms of like how the algorithm does scale. But I would imagine that in terms of complexity, like in terms of the state space, obviously the state space that you have search does grow exponentially, but in terms of the action space, you can modify the RL algorithm, especially like, because like, okay, so it depends on how you sort of, like in the centralized expert, you know, if you do have like a discrete action space, then your action space would grow exponentially, but there are ways to sort of get around that in the sense of basically we used DDPG, which is basically a, like for continuous action spaces, especially we use DDPG, and that allows you to not have, to have only the actions outputted for each agent. And also there's other, like there's another sort of a strategy where we have in the paper, but although I don't talk about, is like basically, you know, for the centralized expert, what you can have is they can only, at each time step, they only output an action for one agent. So these just, so the centralized expert will both choose an agent and also choose an action for that agent. So instead of having the action space grow exponentially, it can grow linearly because, you know, you only need to output one action for an agent for each agent at each time step. And then you can also decentralize this. And we showed that with the experiments that this is also possible and also a great way to reduce the scaling. Yeah, but that is a very good question though, to be honest. And it's also like worth looking at in terms of theoretical guarantees and stuff. Yeah.
Cool, thank you.
Yeah, thank you.
So I want to be conscious of everyone having time for the break coming up in 3 minutes. Any last brief questions? So if not, Urban and I would like to thank all of the speakers very much. I think everyone should give them a round of applause, and also everyone in the audience for the great questions and for your attention. Really fantastic session. Thank you all so much.